MBA 633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this segment, we will be discussing point estimates, the sampling distribution of X bar, which is the sample mean, and a very important theorem in inferencing, which is the central limit theorem. Let's take one of the examples that we had used in the previous clip. So let's say we have a population which consists of all registered vehicles in Virginia, and we'll assume that this population is very large. For all practical purposes is infinite. In other words, capital N, the size of the population, is very large. And I want to know what the average repair cost per year per vehicle is. In other words, I want to know the population mean, the mean repair cost per year per vehicle. I don't know it, I want to estimate it. And let's also assume that I know the population standard deviation represented by the Greek letter sigma, and I know it to be $100. We'll later on discuss under what conditions it's reasonable to assume that we know it. Sometimes we don't know it. What can we do when we don't know it? But to start our discussion off, let's say we have this population, which is the set of all registered vehicles in Virginia. I know that the population standard deviation is $100. In this case, I'm looking at the repair cost per vehicle, and I'm interested in knowing the average repair cost per year per vehicle, mu. So in order to do that, let's say I took a sample of 50 vehicles. I called up the 50 owners. I asked each one, how much did you spend per year on your vehicle? And I get 50 numbers. I take their average, and hence I get a sample mean of $485. Now this $485, it's what's called a point estimate. It's called a point estimate of the population mean. In other words, it's a one number guess of the population parameter that I want to estimate. So if somebody tells me, give me one number that you think is the best, your best estimate for the average repair cost per vehicle for the population, I would say it's $485. Now, what I do know is that $485 is close to the true population mean. It's close to mu, but I also know that I'm likely to be a little bit off. The question is, can I also, in addition to this $485, convey a sense of the degree of uncertainty in the estimate that I made? So can I quantify the uncertainty in any way? Now we will see later on that there are different ways to quantify the uncertainty, but the foundation for computing the uncertainty associated with this inferencing is what is called the sampling distribution of the sample statistic. Remember in the previous clip we said that every sample statistic is a random variable since there's uncertainty associated with it. The population parameter is a constant, of course. Okay, so what the central limit theorem tells us is that if the sample size is large, and for practical purposes a large sample is one that is greater than or equal to 30. If the sample size is more than or equal to 30, then the central limit theorem tells us that the sample mean will be normally distributed. That makes life quite nice and simple for us. So regardless of what the actual cost distribution might be in the population, what we are saying is if the sample is large, then the sample mean will be normally distributed. Okay. Moreover, the mean of this, every normal distribution you know has a mean and standard deviation. The middle of this distribution, fortunately for us, is the population mean. What that implies is that on average I would expect the sample mean to be at the population mean, and that's good for us because if it weren't, then I know there's some bias in my estimation. So I would expect the sample mean to be here in the middle, but I also know that it will stray from there from time to time. How much can it stray? The central limit theorem also tells us that when the sample is large, it's normally distributed and its standard deviation is sigma divided by square root of n. This is very important. Now notice the two inputs here. Sigma is the population standard deviation and n is the sample size. Okay. So intuitively what this is telling us is if the population is itself very spread out, in other words, repair costs of all these thousands and thousands of vehicles are very spread out, then the sample mean will also wiggle around a lot more. Hence, the population standard deviation sigma is in the numerator. The higher the population standard deviation, everything else remaining constant, the more the sample mean will stray, will vary from the middle. Okay. However, I can control for some of that by choosing my sample size. If my sample size gets large, you can see n is in the denominator. Okay, so if n gets large, the standard deviation of the sample mean gets smaller. In other words, I can control how much my sample mean will stray from the true middle by increasing the sample size. So this is very important to remember. Okay, so the bottom line here is that if the sample is large, meaning the sample size is greater than or equal to 30, then the sample mean, which is a random variable, is normally distributed with a middle or a mean of which is equal to the population mean, which I'm trying to guess, and a spread or a standard deviation equal to sigma divided by square root of n, sigma being the population standard deviation and n being the sample size. Okay, so I think this should give you some idea, and just intuitively, n is in the denominator, but notice that it's a square root. So if I want to be twice as precise, I will need 4 times the sample size and so forth. So it gets costly. Precision is costly. Okay, so keep this sampling distribution in mind of the sample mean, and we will, in later clips, we will see how to use that sample mean to quantify our inferencing. In other words, not just give a point estimate, but in addition to the point estimate, be able to quantify our uncertainty in some way. We will see what that way is. Okay. All right, let's move on to the second example that we had in the previous slide. And the second example was the one with the likely voters. Okay, so let's say that the population here is the collection of likely voters in the 2012 election. Okay, again here let's assume that the population is very large, n is very large, infinite for all practical purposes. And what I'm interested in is the population parameter p, and this is the proportion of likely voters who will vote for Romney in 2012. Notice that p is a number between 0 and 1. I just don't happen to know it for sure. It's a constant. If I had enough time and money, I would ask each likely voter and I could get precise value for p with absolutely no uncertainty. It's just that I cannot do it for all practical purposes. So what do? I take a sample of size n. Let's say I talk to 100 likely voters. I ask each one of them, would you vote for Romney? They say yes or no. And based on that, I come up with a sample proportion p bar. And let's say that p bar comes to 0.51. So 51 out of those 100 people said, 100 people in the sample said they would vote for Romney. So this sample proportion p bar is my point estimate of p. So if somebody asks me, give me one number which is your best estimate of the proportion of likely voters who will vote for Romney, I would say 0.51. But just like with the previous example, with this point estimate, I'm not able to convey a sense of the degree of uncertainty associated with that inferencing. Okay. Now, just like with the sample mean, just because the sample proportion is also subject to uncertainty, it's a sample statistic, so it's uncertain, so it must have some kind of a distribution, a pattern of uncertainty. If it's uncertain, it must have a pattern of uncertainty. So what is that pattern of uncertainty? Here again, we are lucky if certain conditions hold, and those two conditions are the following. If small n times p is greater than or equal to 5, small n is the sample size, p is the population proportion that I don't know. If n times p is greater than or equal to 5, or n times 1 minus p is greater than or equal to 5, then the sample proportion is normally distributed with the following parameters. The mean is p, and the standard deviation is p times 1 minus p divided by n square root. Okay, so the sample proportion is again normally distributed provided that these two conditions hold. If those two conditions hold, the sample proportion, which is a random variable, is normally distributed. It's bell-shaped, okay, and its middle is the population proportion, and that's very nice because it means on average I expect the sample proportion to equal the population proportion. That's nice to know. It's reassuring that it's an unbiased estimator. And how much will the sample proportion stray from the middle? How likely is it to wiggle? In other words, how uncertain could I be? One indicator of that is the standard deviation of this normal distribution. The standard deviation is given by square root of p times 1 minus p divided by n. Okay, that's the standard deviation. Once again, notice that this p, the population proportion, is in the numerator, and just as before, n is in the denominator with the square root. So if I increase my sample size, I can shrink the standard deviation. In other words, make this curve more peak. In other words, with a larger sample, I can be more certain about the inferencing that I do. Notice that in each of these two examples that I've discussed so far, I haven't yet shown you how to do the inferencing. I have simply laid the foundation for quantifying the uncertainty and doing the inferencing. In other words, estimating the population parameter based on the sample statistic, and that foundation is the sampling distribution of the sample statistic. If I'm using x bar, the sample mean, to estimate the population mean mu, I will use the distribution of x bar to quantify my uncertainty. If I'm using the sample proportion p bar to estimate the population proportion p, then of course I will use the sampling distribution of p bar. And what the central limit theorem tells us is if the sample size is large, if n is greater than or equal to 30, then the sample mean is normally distributed with the mean and the standard deviation that we mentioned in the previous worksheet. And if these two conditions are met, n times p greater than or equal to 5, n times 1 minus p greater than or equal to 5, if those two conditions are met, then the sample proportion is normally distributed with the mean equal to p and the standard deviation equal to square root of p times 1 minus p divided by n. Okay, so keep these two sampling distributions in mind. The main thing to remember here is that every sample statistic has a pattern of uncertainty because they're random variables, and we use that pattern of uncertainty, in other words, the sampling distribution, to quantify the uncertainty. How to do the quantification we will see in subsequent instructional clips.